So a really important idea in acid-base chemistry is centered on the amphiprotic nature of water, which I alluded to in a previous video. So amphiprotic means you have a molecule that can accept and or donate a proton, which means it can act as an acid or a base. And if that's the case for water, it can act both as an acid and a base, then the logical deduction would be that it can react with itself, and it can, and that process is called the autodissociation of water. Auto meaning automatic. So it just happens. So when water is with itself, if it can behave both as acid and base, then it's automatically going to react with itself both as an acid and a base. So what does that look like? Well, it literally just means a water molecule reacts with a water molecule. One of them acts as an acid, one as a base, and you get a corresponding conjugate in acid-base pair. So we have H3O plus, the conjugate acid, that's water plus that proton. That proton was stolen from the acid and went to form the hydroxide. So very quickly, we could use the same relative strengths of conjugate acid-base pairs in the table that we just used to assert that, well, H3O plus is here, and the other acid is H2O, which is down here. So H3O plus is much stronger as an acid. Same thing could be said in terms of base comparison. Hydroxide is much stronger than pure water. And based on that logic, we would say that the equilibrium would lie very far to the left. And that's exactly what it does. So let's talk specifically about that equilibrium constant for the autodissociation of water. Because it's so important, it gets sort of its own branding. So we still use the capital K, but we give it a subscript of W because it's water. And see if you can write out what the equilibrium expression would be for the autodissociation of water. And let me note that these are pure substances because it's water, and these, of course, are aqueous. So see if you can pause that and write up what the equilibrium expression would be. Okay, cool. So you should have ended up with something like this. Remember, we're talking about equilibrium, not kinetics, so big K here. That's the ratio of the products raised to the coefficient divided by the concentration of the reactants. But we do not include pure substances, so water doesn't end up here. And we only have stoichiometric coefficients of 1, so we end up with just the hydronium ion concentration times hydroxide concentration. It turns out that the actual value for Kw at room temperature 25C is 1 times 10 to the minus 14. So knowing what you know, is that a big number or a small number? Well, it's super tiny, which means that the concentration of these two ions, the products in this reaction, taken together is super small. Does that support our original assertion just based on the relative strengths? Yeah, it does. It says that, well, at equilibrium, the concentration of these two things together only has a product of this, which means that most of the system is in pure water form, meaning the equilibrium position is far, far, far favored to the left or towards pure water. But it does mean that the glass of water that's sitting around the room or the bottle of water, wherever you see water around you as you're watching this video, it does mean that that system at equilibrium does have some amount of ions. It's automatically reacting with itself via the autodissociation reaction, but it does so in a way that at equilibrium, there's a really small amount of those things. And that's why pure water, when you remove all the ions from it and all the minerals that come naturally and you filter it, pure water is non-conductive. If you were to stick a battery and a couple wires in series with a light bulb into water, it would not conduct electricity. And that's because there are ions here which could carry that electricity, but there's such small concentrations that they're negligible. And in order for water to actually serve as a conductor, we need other ions present, the things that you would find dissolved minerals, things like chloride and bromide and nitrate and sulfate, etc. So now that we know this, could we figure out what the concentration of each of these individual ions is at 25C in pure water? Well, yeah, we could just do an ice table like we've done before. We could just say, well, we're starting with pure water, so it doesn't have a concentration, so I'll just put some squigglies there. It's not relevant. And we'll just say that before we've allowed the system to reach equilibrium, so the initial condition, we don't have either of these. So we're talking about the autodissociation. We don't have any yet. The change means it's negligible or it's not important because they're pure substances, but based on the stoichiometry, we would expect some amount x of both of these things to increase in concentration. So that means the equilibrium concentration should be x, and we can take those x's and feed it back into the expression for Kw. So that should look something like this, which means 1 times 10 to the minus 14 is equal to x squared. So the root of 10 to the minus 14 would be equal to x, which is 1 times 10 to the minus 7. So that means that the equilibrium concentration of a glass of pure water, nothing else in there, just thinking about the autodissociation water, it's about 10 to the minus 7 molar, moles per liter. Remember, 10 to the minus 6 is micromolar. So we're talking about 0.1 micromolar is the concentration of H3O plus and hydroxide ion when we simply allow water to react with itself. Maybe the more important takeaway here is that this reaction is always true. Anytime you have water, it will react with itself through autodissociation. But often we're talking about acids and bases in water. And so when we're thinking about what happens when we have a strong acid in water, we're including the fact that this reaction is happening as well. And in reality, when we dump in a whole bunch of strong acid, what we're really doing is a Le Chatelier's principle type equilibrium shift, where we're adding a whole bunch of strong acid, which is going to shift the equilibrium. So a follow-up example of that would be, what if you went and you measured some water at an acid mine drainage site, and you determined that the hydronium ion concentration there from other acids, right, because pure water wouldn't yield this result, but other things are in the water, which makes the H3O plus concentration 1.4 times 10 to the minus 7. Could we figure out then what the corresponding hydroxide concentration? Well, yeah, because we know that Kw is always true. It has to be true. So let's start by writing up what Kw is. So Kw is the product of the concentrations of hydronium and hydroxide, always going to be true, and it's always at 25C going to be equal to 1 times 10 to the minus 14. What we're figuring out from this example is that the strong acid from this acid mine drainage is making the hydronium ion constant quite a bit higher. If this has to be true, this has to be true always in water, then what does that mean for hydroxide? Well, it just means that the product of these two things can still equal 10 to the minus 14. So if the hydronium ion concentration is really high, then that means by default the hydroxide ion concentration has to decrease by a corresponding amount such that this equilibrium expression remains true. So we could simply solve this. So we would just take the Kw and divide by H3O plus because we know it, and that would give us hydroxide. And so that's 7.1 times 10 to the minus 11. So is this system acidic or basic? Well, it turns out that really it's just the relative concentrations of hydronium and hydroxide that define that system. We can infer from the question that this is acid mine drainage, so this is probably acidic. But remember, for pure water, what the concentration of each of those, so pure water, it was 10 to the minus 7. That was both hydroxide and H3O plus, right? That's what their concentrations were. And what we found is that in the acid mine drainage system, the concentration of hydronium ion was considerably larger, right? That's the smaller exponent here, 10 to the minus 4 versus 10 to the minus 7. It's about 1,000 times higher concentration of hydronium ion concentration, and correspondingly then about 1,000 times lower concentration of hydroxide. And it's the ratio of these two things that tell us whether the solution is acidic or basic. It's neutral. It's neither acidic or basic when they are both equal to 10 to the minus 7. That can only happen when you have pure water. And when you have more H3O plus than OH minus, then you have an acid, and vice versa for a base. So that idea brings us to what we, I think, already colloquially know as the pH scale. And the pH scale is simply a measure of these two species, H3O plus and hydroxide.